There we go. Okay. So what do I want to talk about today? We're going to just look at what is a datum anyway. What are global datums versus local datums? Static versus time-dependent reference frames. And between 1994 and GDA 2020, what actually changed? And then just a quick mention about accurate and complete coordinate reference system metadata and complete attribute data on GIS files. So a datum, when we're talking about a mapping datum, obviously, we mostly refer to geodetic datums, which is a global reference frame for precisely representing the position of locations on the Earth or other planetary bodies by means of geodetic coordinates. And a datum consists of three parts. There has to be an ellipsoid, an origin, and control points. So if we look at this sketch of an ellipsoid, the red outline is the Earth's actual shape. So it's not a perfect sphere or spheroid, whereas an ellipsoid, or the other word is a spheroid, is a mathematical representation, is a mathematical model to try and represent the Earth's shape. So in some areas, like over here, it fits the Earth well. In other parts on the other side, it doesn't fit well. So that is one of the reasons why we have local datum definitions. The origin that has to go with the ellipsoid is the point, or is where the ellipsoid or geoid is tied to a known, and it's often a monumented, physically monumented location on or inside the Earth. It's not necessarily at 0 lat 0 long. So the other thing to note is that while the center of the Earth's mass is over here, this is the center of the ellipsoid or spheroid. Here we're talking about geocentric, center to the center of the Earth, and here we're talking about geodetic, so relating to the map system. And then you also need a bunch of control points that have been precisely measured from the origin and are also monumented. So we have global datums and we have local datums. The global datum that everyone's familiar with is WGS84, which pretty much became popular when we started using the GPS system. It's both an ellipsoid and a datum. But because the Earth is an imperfect ellipsoid, local datums can still give you more accurate representation than WGS84 can. WGS84 is to an extent a bit of a generalization. So that's why we still have local datum definitions, such as in Australia, we've got GDA 94 and GDA 2020 now. In South Africa, we had the Cape datum, and 1994, we had the Hartbeespoort datum, which was our local definition of WGS 84. In North America, you've got NAD 83 and NatRef 2022. In South America, the provisional South American datum, the South American datum, and now we've got CIRGAS. So these things don't go out the window, because they are still more accurate in their little area of interest than WGS 84 can be. Then we also have static datums and time-dependent datums. So most local datums, including GDA 2020, are static. So the position of mapped features like roads, rivers, property boundaries do not change over time, regardless of ongoing changes in the Earth's surface due to plate tectonics. The big thing here is plate tectonics. Whereas, like I said, with the rise of WGS 84, it's because we started using the Global Navigation Satellite System, or GNSS. And that is what makes up the GPS system, or the GPS as we use that system. These things base their coordinates on a reference framework that is fixed to the center of the Earth. So it's a geocentric system around which the satellites are orbiting, in which the positions of features change with time due to plate tectonic motion. So these satellites that we use are geostationary. They never change their position with regards to the Earth itself. And they are orbiting around the center of the Earth, the geocenter. So in this context of static versus dynamic datums, GDA like I said, is a static one, but the Australian Terrestrial Reference Frame 2014 is the dynamic version, which means that coordinates of an object change over time. And in specifying such coordinates, you can't just specify X, Y, and Z. You also need to specify a date stamp in the epoch format. So the epoch format, for instance, today's date and time was about 9:45 this morning, is 16696866377. So it measures time from the 1st of January 1970, which is when a bunch of programmers just arbitrarily decided, okay, we're going to start there for no reason. So this system is useful for extremely precise positioning in applications such as self-driving vehicles or other extremely precise location-based services. It's not something that you're going to be using to do your exploration and mining, because there you don't want your coordinates to be changing over time. You want them to be the same for at least 30 years until the next static datum is redefined. So GDA 2020, the advantage of it is that it is more closely aligned to the global navigation satellite system, and therefore achieves maximum benefit from accurate positioning, suitable for projects with a longer lifespan, such as big construction projects or a mining operation. Then we also have these concepts of geographic versus geocentric. So the geodetic or geographic latitude is the angle between the equatorial plane and the normal to the ellipsoidal surface at the considered point. So this little graph just shows it. This is your geodetic latitude. It is measured based on that normal to the Earth's surface, or to the surface of the ellipsoid there. Whereas a geocentric latitude is actually measured from the center of the Earth. So geocentric coordinates are different to geodetic coordinates in terms of the latitude only. The longitude is not affected. So to conform to the GNSS, some countries are changing to geocentric datums, and that is what the GDA 2020 is. It's a geocentric datum to be more closely aligned with the GNSS. So what has actually changed from 1994 to 2020? When most of our local datums were adopted back then, local accuracy differences in positioning of 1 meter or so were unimportant, because you could only get 5 to 10 meters accuracy out of a GPS system anyway. And the GPS positions were only accurate within 100 meters. So who cared back then? But now, positioning technology has evolved considerably. If you look at your mobile phone and you're using Google Maps, and you can exactly map where you are, on which side of the road you are, it's that accurate. And the big thing is that continents are moving due to plate tectonics. And Australia, with its mullet flapping in the wind and its Mo for Movember, is the fastest mover of all on the planet. So since 94, these are the average movements of the continent. Tasmania and the East Coast being the slowest at 1.5 meters difference. And then pretty much the whole of WA has moved at 1.8. So the whole of the continent is moving that way, but it's also rotating a little bit around Tassie. So why this obsession with new datums? It's because now we're going to start noticing discrepancies between modern location measurements and things that were mapped back using GDA 94, or in the South African context, Hartbeespoort 94. So the Australian government committed $225 million to provide 10 centimeter or better accurate positioning in all of Australia, which is a significant improvement from the 5 to 10 meters accuracy you can get pretty much before GDA came along, GDA 2020. So the upgraded GDA 2020 ensures that spatial data can be more closely aligned to positions observed using the GNSS, the Global Navigation Satellite System. And Australia is not the first, or not the only one, but is the first, because the Americans are also now ditching the NAD 83 datum in favor of new systems that are coming out, well, being defined this year and will be rolled out in the coming years. The NatRef system, North American Terrestrial Reference Frame, the Pacific one, the Mariana one, and the Caribbean one. So they've decided to divide their territories into 4 datums that are also going to be static datums, but which will be more suitable for each of these different areas of their territories. So that's pretty much it for datums. Then just a little spiel about accurate and complete coordinate reference system metadata. So any decent GIS system can accurately place a vector or raster or other spatial objects like tins, CADs, whatever, on the planet as long as the coordinate reference system is properly defined. So for a shapefile, for instance, an Esri shapefile, which is the old format for your ARC stuff, the information is stored in the associated .prj file or projection file, which is a simple text file and contains what we call well-known text, WKT format. So an example of a simple lat long or geographic definition, it just gives the datum, the spheroid, the inverse flattening coefficient, prime meridian, and the degree. Whereas if you look at a projected system below UTM zone 33 south, then it's giving you a lot more of information. What is the projection system? What is the datum, the spheroid, and a whole bunch of other parameters which are necessary to define a UTM zone. And typically, the most common type of data, GIS data that we're given by our clients are tenement polygons, and hopefully that will soon fall by the wayside for Australia as we move to using the land monitoring system that Laurel mentioned before, where we'll be automatically pulling these things from the various Australian states. But for everywhere else in the world where we can't do that, we'll still be relying on client shapefiles of tenements. The problem is that if only a partial file is provided, then we can't really use it. So if you look at an Esri shapefile, can be up to 14 separate files, all with the same name. But at the very least, you need the .shp, shx, prj, and dbf. Whereas for map info tab files, we need tab, map, dat, and inf. If no CRS data is included in the GIS file, so you give me something that is only a dbf, a shakes, and a shape, no prj, then the GIS will still be able to draw the shape, but it has no idea where on the planet to put it, or at which scale. So it will draw the shape, it'll be exactly the same size as the whole Earth, and we can't do anything with that. On the other hand, if there is no information in the dbf file or the attribute data, then we can draw the shape, we can place it, but we have no data tied to it. So tenements like the tenement ID, grant date, expiry date, etc. And of course, the impact of an incorrect CRS or coordinate reference system can be quite hectic. There's no room or time for guessing a GIS vectors system. There are just too many possibilities. A datum shift, and this happens quite a lot when a country is changing from one datum to another. So in South Africa, when we changed from Cape to Hartbeespoort, and people would not define the datum, and you would assume it's in one datum, but in fact it's another datum. Then you could be out by as much as 300 meters. So you're never going to find that borehole again. In exploration data, 300 meters is significant, but in a production environment, a displacement of 1.8 meters, which is the difference between GDA 94 and GDA 2020, could be equally disastrous because you're mining a reef that might be that thick, and now you're in the wrong space, and you put your mine infrastructure in the wrong space. Your block modeling and your ore blending, etc., are affected as a result of that. So it's much easier also to spot a massive shift than it is to spot a small one, but the consequences could be equally detrimental. And that's it from me. Any questions?